In today's lecture, we're going to continue talking about partitions. In the last lecture, we saw that the number of partitions of a set with m elements of a particular type, say m1, m2 through m sub n, that means we're partitioning the set of m elements into n non-empty pieces, where the pieces have sizes m1 through mn, is given by this formula, where we have the distribution number m1, m2 through mn, divided by this product of factorials, where here R1 is the number of these m's, which is 1, in other words, the number of pieces of size 1, R2 is the number of pieces of size 2, etc. This was just standard problem 15. Well, what if we wish to count instead the number of partitions of a set into some fixed number of non-empty parts? We don't care what the different types are, we just care that the set is being partitioned into 4 parts. And whenever we talk about 4 parts, we're talking about non-empty parts. If one part is empty, it's really partitioned into, say, 3 non-empty parts, plus an empty one. We're not going to be counting things like that. We'll be always talking about non-empty parts. We'll give a name to it before we start computing it. We'll call that number of partitions of an m element set into n non-empty sets. We'll call that SMN. These numbers, SMN, before we even start computing them, these are called Stirling numbers of the second kind. Now you might think it odd we're talking about Stirling numbers of the second kind, and in our course we're not going to be talking about Stirling numbers of the first kind. They come up with combinatorial explanations as well. They come up when you want to count the number of permutations with a fixed number of cycles. They also come up algebraically when you're talking about something called a declining factorial. They give you the coefficients that come up when you expand a declining factorial, n times n minus 1 times n minus 2, etc. For us, we'll be talking about these Stirling numbers of the second kind, or we'll call them the S numbers. Here's standard problem 16. How many partitions are there of a set with m elements into n non-empty parts? And we can just write down the answer right away, not a closed form formula for the answer, but in terms of the t numbers. SMN is just the same as TMN divided by n factorial. And it's pretty easy to see this, because we can make this one-to-one correspondence, actually not a one-to-one correspondence, an n factorial to 1 correspondence between distributions of, say, m distinct balls into n distinct boxes, and partitions of an m element set, that means a set with m distinct elements, into n non-empty parts. And I'll show you how that works. Let's say we want 5 balls. You can think of this as a 5-element set. I'm drawing it as balls so that we can use it to talk about either S or T numbers. But think of this as a 5-element set. And I'm going to show you a partition into 3 non-empty parts. Well, let's say I have ball 1 and ball 4, ball 2 by itself, and ball 3 and ball 5. You could talk about this with set notation. You're partitioning the set 1, 2, 3, 4, 5 into these 3 non-empty sets, the set with 1 and 4, the set with 2, and the set with 3 and 5. The reason I'm writing this with balls is I claim this partition will correspond to 6 different distributions of these m balls into 3 boxes. Here's one. I could think of box A here, box B here, box C here, and maybe A will get the 2 ball, B will get the 1 and the 4, and C will get the 3 and the 5. That's one possible distribution. Oops. Let me change that. What are the other distributions? Well, we could just relabel the boxes. I could instead call this box B, this box A, and this box C. Or I could call this box A, this box C, and box B. Or I could have this box B, this box C, this box A. There are clearly 6 ways to rearrange these. I could have this as box C, this as box A, and this as box B, or C, B, A. Regardless of where I put labels on the boxes, we can always think of this set being split up into these exact same 3 subsets. So these 6 different distributions would correspond to just a single partition. So we divide the number of distributions by 6, which is 3 factorial. In other words, they're T53 distributions. We divide that by 3 factorial, which is 6, to get S53. So we already know T53. We've computed that in class. That's 150. S53 is just that 150 divided by 6, which is easily seen to be 25. Here are some important special cases. What is SM1? Well, this counts the number of ways you can partition an M-element set into a single non-empty part. The whole set. One way to do it. That's just one. How many ways are there to partition an M-element set into M non-empty parts? Well, again, there's only one way to do it. What is that way? Just M singleton sets. Each individual element in its own set. That's the only way to do it. Note here, TM1 was also 1, and thus SM1 is just TM1 over 1 factorial. It should not surprise us that the answer is 1. Similarly, we had TMM is M factorial, so using the formula from earlier, SM M should be M factorial, that's TMM over M factorial, which is just 1. What about SM2? Well, how many ways can you take a set? Let me give you just an example here. 1, 2, 3, 4, 5. And partition it into 2 non-empty parts. Well, there's going to be a simple trick that will help us count this very easily, though there are many ways we could go about doing it. Let's say that I'm number 3. I'm interested in number 3. The number 3 has to be in one of the 2 parts. So we partition. So we have one part here that contains the 3, and we have the other part here, which has to be non-empty. Here's a question for you. How many ways can I choose what other elements go in this set with the 3? Well, there are 4 remaining elements in our set other than the 3. I can pick any subset of those to go along with the 3. Well, is that really true? The only subset I can't pick would be the subset that contains 1, 2, 4, and 5, because then there would be nothing left for the other set. So really, to go along with the 3, to partner up with the 3, I'll say, we can pick any subset of 1, 2, 4, 5, other than the full set 1, 2, 4, 5 itself. For example, if I put the empty set in there, I would put 1, 2, 4, 5 in this other set. If I pick the set with 2 and 5, let me just put those here, then I would have 1 and 4 here. So the total number of ways to partition the set is just the number of subsets of a 4-element set, which is 2 to the 4th, and we have to take away 1, because one set, the full set of remaining elements, is not eligible. In general, for an M-element set, just think of any one element as the one we're going to talk about. How many ways are there to find partners for this one special element? There are m-1 remaining elements, thus there are 2 to the m-1 subsets of that set. The only one that we can't use to partner up with our special element is the one that contains all the other elements, so we subtract just a single one. Finally, what about SMM minus 1? Again, let's look. If I have this at 1, 2, 3, 4, 5, I want to partition this into 4 pieces. Well, how many ways can I do that? The only way you can take a 5-element set and partition it into 4 pieces is if 3 of the pieces have size 1 and 1 has size 2. And this partition will be completely determined if you tell me which 2 elements, I don't know, say 1 and 4, go into the set with 2 elements in it. Say 1, 4 there. The others have to be singleton sets with the other elements. 2, 3, 5. Well, how many ways were there for me to pick 2 elements to be paired together? Exactly 5 choose 2. In general, for an M element set, there would be M choose 2 ways to pick 2 elements, and thus SM, M minus 1 is exactly M choose 2. Also remember, in both of these cases, we already showed the T numbers. TM2 is 2 to the M minus 2. SM2 should just be this divided by 2 factorial, which is 2, and that gives us this formula. Very quickly, we also showed that TM M minus 1 is M choose 2 times M minus 1 factorial. We just take this and divide by M minus 1 factorial, and clearly we get M choose 2 for SM M minus 1. So you can just find new combinatorial explanations for these formulas, which you should be very comfortable with. Or, if you know all about the T numbers, you just divide TMN by N factorial, and you get these special cases right away. Using those special cases, we can easily construct an S triangle that's just like our T triangle. We're going to start with row 1. Just has 1. That's S1, 1. Row 2 will be S21, which is always 1. And let me remind you of those identities. SM1 is always 1, as well as SMM is always 1. That means that any row in this S triangle will start with a 1, and it will end with a 1. We also know SM2 is 2 to the M minus 1, and SM M minus 1. This is the second element, and the second to last element is M choose 2. So, starts with a 1, ends with a 1. The second element, we can use either formula. 2 to the second power minus 1 gives us a 3, or we could just use 3 choose 2, which is 3. That goes here. For row 4, it starts and ends with a 1. For the second position, we have 2 cubed minus 1. For the third position, we have M, which is 4, choose 2, which is 6. And let's go through that now for row 5. It starts and ends with a 1. That's from these two. In the second position, we have 2 to the 4th minus 1, which is 15. In the fourth position, we have 5 choose 2. 5 choose 2 is just 10. And S53, we actually computed that just a few seconds ago. S53 is 25. So here we see the first 5 rows of the S triangle, and you can continue row after row after row, either knowing the T triangle and converting to S numbers, or using some other method to compute the S numbers directly. Can we come up with a recursive formula just the way we did for the T numbers that will work for the S numbers? The answer, of course, is yes. It's a little tricky here to see it, but here's one way to start. This 15 is 1 plus double the 7. The 7 is 1 plus double the 3. 3 is 1 plus double that 1. So you can see each member of this diagonal is just the one up and to the left plus twice the one up and to the right. But it's not the same for this next diagonal. 25 is 7, plus now you need 3 6s. 6 is 3 plus 3 1s. This 10 is 6 plus 4 1s. That kind of suggests a pattern like this. SMN, the number in row M, position N, is just what you get when you go up left Sm minus 1, n minus 1, plus n, the position number, in this case 2, in this case 3, in this case 4, etc., times the number that's up and to the right. So S53 is 25, that's 7 plus 3 times S43, which is 6. And this formula can easily be shown to be true in a couple of different ways. Now, both of the ways for proving this formula are in the homework, and I want you guys to work these out on your own. Let me just describe what the two methods are. One method is write everything on the right, write everything in both sides in terms of the t numbers and verify that this is true. What is Smn in terms of t numbers? Well, it's tmn over n factorial. Write these in terms of the t numbers and verify that's true, and you'll need to use the recursive formula for the t numbers to demonstrate that this is true for the s numbers. That would be what I call a purely algebraic proof using our result from standard problem 16. Another method is to just give a combinatorial proof. Ask what these count. Well, we know what Smn counts. That counts the number of partitions of a set of size m into exactly n non-empty parts. Well, how are we going to show that that's equal to the sum of these two terms? The suggestion in the homework problem is think of one preferred element and ask who joins it, just as we did earlier when we were computing Sm minus 1. And you'll find that you can break it down into two cases and get this result. I want you to really think about it and try to get a complete proof on your own.